Hi, I'm Hao-Wei Chen. Welcome to the presentation of Cascaded Local Implicit Transformer for Arbitrary Scale Super Resolution, which can be abbreviated as CLIT. In this work, we propose the local implicit transformer as a solution for arbitrary scale SR tasks. LIT utilizes the local attention mechanism to prioritize nearby information for generating high-quality HR images. Additionally, instead of aggressively upscaling LR images to HR images in a single step, we introduce a cascaded version of LIT to gradually upscale the LR images. To better accommodate this newly proposed architecture, we further develop a cumulative training strategy. First, I will give a brief background introduction about recent learning-based arbitrary scale SR method. Recently, a paper called LIF has incorporated the neural implicit function to learn the continuous imagery representation, enabling image upscaling at arbitrary scales. In this research, HR coordinates, cell size, and latent embeddings are fed into MLP, which is acting as implicit functions. The MLP then estimates the RGB value corresponding to the query HR coordinate independently. Then, I will talk about our motivation for this work. Since the RGB values are predicted independently, this continuous pattern will appear. To overcome this issue, they propose the local ensemble technique to weighted sum the RGB value of all surrounding pixels around the query HR coordinate. However, this kind of interpolation only considers the related distance between these coordinates and disregard feature similarity. As a result, the quality of prediction might be degenerated. In the provided example with 2 rows of pictures, we can observe that the edges in prediction are blurry or even exhibit incorrect patterns. In order to account for feature similarity, we design a local attention mechanism. In particular, feature correlation will be considered because of the nature of the attention mechanism. Furthermore, these feature correlations are within a predefined local window, rather than only for surrounding pixels. In a provided example with 2 rows of pictures, the sharp edges are presented in correct pattern. Here, I will introduce our proposed method. This is the overview of our proposed architecture. The major component LIT is placed in front of the MLP decoder. In this slide, we formulate the problem into equation associated with LIT module. Our goal is to learn the residual between the ground truth HR images and the interpolated HR images. The inputs of LIT modules are latent embedding, sets of related coordinates, and the cell size. Based on these inputs, we apply the local attention mechanism to consider the feature correlation and related distance together. It is essential to understand the process of creating the local grid, which is utilized to calculate local feature similarity. Initially, we start with LR pixel coordinates as an example. Then, we overlay the HR pixel coordinates on top of it. To this end, we select a pixel of HR coordinates as our query coordinate. Then identify its nearest LR pixel coordinates. Finally, we take these nearest LR pixel coordinates as the center and expand the local grid based on the predefined grid size. By following this procedure, we finish the construction of the local grid. We apply the local sampling to the key and value features, and perform local attention mechanism over the predefined local grid to generate local latent embedding. The feature correlation is obtained by the operation of inner product. As for related distance, we add a related positional bias to the output of inner product and produce local attention map through softmax operation. Upscaling LR images to a significantly larger HR image, such as by a factor of 30. A one-step reconstruction can be too challenging and aggressive. Following this idea, we propose a cascaded framework called CLIT, that divides the upscaling process into multiple steps. In CLIT, there are multiple stages, each stage responsible for a different upsampling factor. For instance, the figure demonstrates the scenario of upscaling the LR images by a factor of 30. In stage 1, one time LR image will be upscaled to 30 times HR image. In stage 2, we further upscale 4 times LR images to match the 30 times HR images. Finally, in stage 3, we upscale 16 times LR images to achieve the 30 times HR image. The outputs of each stage will be summed up to obtain the final HR image. Due to the modifications made to the architecture, our model can handle a wide range of upsampling factors, ranging from 1 time to 30 times. However, the performance will decline with training the model directly with the upsampling factor, which is uniformly simple. To overcome this challenge, we designed a cumulative training strategy. The core idea is to alternatively switch between training with small and large upsampling factors. In the provided figure, we first train the stage 1 LIT as usual. Once the training of first stage is complete, we incorporate the second stage of LIT into the training process. At the same time, the upsampling factors are alternately switched between small and large values. This pattern continues for subsequent stages as well. After knowing the proposed method, I will demonstrate the experimental results. This is the figure that compares qualitative results of CLIT with other baseline methods, LIIF and LTE. In the first row, it can be observed that our results exhibit enhanced continuity and sharpness in the representation of alphabets, particularly for the letters M and S. Moving to the second row, our results successfully preserve the checkerboard pattern and are closer to the ground truth image. In the last row, our results accurately depict the red lines on the flag, while the other baseline failed to do so. As we leverage the attention mechanism, it becomes possible to visualize the attention maps, providing insight that where the model focuses attention. In the second column, the upper left corner displays the local attention maps around the red dots, which clearly align with the patterns present in the images. This alignment indicates that the attention mechanism effectively captures the textures and assists in generating favorable results. If you are interested in more detailed results, we provide another video demonstration on YouTube. As for quantitative result and unblended analysis, please refer to our paper. Thank you for your time.